Hello my friends and welcome back to the You Can Do TV channel. This is about the machining process of rollers for hot rolling mills at Vítkovice, Slavarny. After centrifugal casting using Gonterman Piper's technology, the rollers undergo rough machining to remove excess material and achieve the initial shape. This is followed by heat treatment to enhance hardness and wear resistance. Subsequent precision machining refines the surface and dimensions, ensuring adherence to strict tolerances. Advanced grinding techniques further improve surface finish and roundness. Depending on the required properties, additional treatments such as induction hardening or deep rolling may be applied. Rigorous quality control, including non-destructive testing and dimensional inspections, ensures each roll meets industry standards. The facility's expertise allows for continuous material innovation, optimizing performance and longevity in demanding rolling applications. A thermal lance was used to cut up the FPSO turret bearing for disposal. The bearing, primarily made of carbon steel with heat-treated rollers and an inconel overlay, required a high-temperature cutting method. The thermal lance operates by igniting iron rods inside a conduit pipe, while oxygen flows through, sustaining combustion at temperatures up to 4,000 degrees Celsius. This extreme heat efficiently melts and oxidizes the metal, allowing for rapid cutting through even tough materials like the inconel overlay. As the conduit and rods burn away, the operator replaces the consumed section to continue cutting. This method provided a quick and effective way to dismantle the large and hardened bearing, facilitating its removal from the FPSO turret. KUKA robots for the welding industry utilize advanced automation to execute precise and efficient arc welding. These robots are equipped with high-precision motion control and adaptive sensors, enabling them to perform MIG, MAG, and TIG welding with consistent quality. Integrated with welding function packages, they ensure seamless operation and high repeatability. The robots are programmed to follow predefined welding paths while adjusting parameters in real time for optimal performance. Smart networking capabilities allow integration into digital manufacturing systems, enhancing efficiency and flexibility. KUKA's robotic welding systems provide automated solutions for industries requiring high-quality, repeatable welds with minimal manual intervention. The roundo angle roll operates with 3 precision-driven rolls that apply controlled pressure to bend profiles accurately. The rolls adjust dynamically to accommodate different section sizes and bending diameters. The machine exerts force through hydraulic or mechanical systems, ensuring smooth and consistent deformation. Side support guides enhance precision by minimizing material distortion. The R-Series handles various profiles, including angles, T-sections, and U-channels, bending them to precise radii. Advanced automation ensures repeatability and efficiency, while heavy-duty construction allows for high-strength material processing. Optimized for both easy and hard-way bending, it delivers superior results across multiple applications. The roundo angle roll R13S efficiently bends HEA 650 profiles in the hard way using a robust structure for precision and reliability. Its advanced hydraulic system enables smooth movement and variable speed. Equipped with the WCNC4 system, it offers profile libraries, automatic bending cycle calculation, self-correction, and interpolation axis for creating multi-radii shapes seamlessly. This section is about production of dished ends at Hemash. A flat metal plate with a circumference of 13,502 millimeters is cut to the required dimensions before positioning in the flanging machine. The initial pressing secures the plate for shaping. Flanging starts as the knuckle roll applies force along the edge, forming the dish with an inside diameter of 4.3 meters. The proportional hydraulic system ensures uniform pressure distribution, minimizing thinning. The Siemens CNC Total Gap Control continuously monitors pressure and position, optimizing precision. Material thickness after forming is 36.6 millimeters, controlled through automated adjustments. The knuckle roll shaft tilts to compensate for spring back, ensuring accurate shaping. Linear guides maintain axis tolerance even after years of operation. Rotation torque monitoring prevents overloads, protecting both the workpiece and the machine. In the final phase, the flanging machine refines the curvature, ensuring a smooth surface. The completed dished end undergoes quality inspection before use. The FKB 3-roll bending machine operates using the 3-roll bending principle, where the top roll is fully supported along its length. This ensures exceptional precision, crucial for forming tight radii. The innovative Bendtronic control software optimizes bending sequences, enabling high accuracy and consistency. Small top roll diameters allow for the precise shaping of aerospace components. The machine applies a maximum force of 3,700 kilonewtons, accommodating plate widths from 2,500 millimeters to 13,000 millimeters and thicknesses from 4 millimeters to 9 millimeters. Designed for efficiency, the FKB ensures compliance with the strictest tolerance requirements in metal forming applications. The FMB-20 flanging machine operates with a fully hydraulic system, ensuring precise and efficient edge flanging. The workpiece is easily loaded onto the machine, where CNC-controlled automation guides the flanging process. The knuckle roll tilts while the rear cylinder adjusts positioning, allowing uniform pressure distribution. The machine's robust steel components and low thinning technology maintain material integrity during bending. The operator-friendly control panel simplifies adjustments, ensuring high quality and fast flanging. The hardened steel rolls and hydraulic precision contribute to durability and reliability, making it ideal for consistent edge forming. This combination of automation, control, and sturdy construction results in an efficient, high-performance flanging process. The wire and tube fabrication industry plays a crucial role in manufacturing across sectors like automotive, construction, aerospace, and medical devices. The global wire and cable market was valued at $204 billion in 2023, with expected growth at a CAGR of 5.1% through 2030. The tube fabrication market, including cutting, bending, and welding, is projected to surpass $110 billion by 2028. Key materials include stainless steel, aluminum, and copper, processed through CNC bending, laser cutting, and automated welding. The industry heavily relies on high-speed tube mills and precision wire forming machines, enabling mass production with tolerances as tight as plus or minus 0.05 millimeters. Rising demand for electric vehicles and renewable energy is driving further innovation in lightweight and high-strength materials. The horizontal induction machine operates by generating an electromagnetic field within its stationary stator. This induces a current in the rotating conductor, creating a magnetic field that interacts with the stator's field, producing torque. The rotor spins smoothly without physical contact, ensuring efficient, frictionless motion. Speed is controlled by adjusting the input frequency. This design enables high reliability, minimal maintenance, and efficient power transmission in various industrial applications. The Hostler VRM4 roll plate bending machine ensures high precision and efficiency in heavy-duty offshore applications. Featuring an advanced in-feed roller table system and high rotation speed, it enables seamless bending of large diameters up to 15 meters with a load capacity of 150 tons. The patented upper and side supports enhanced control, ensuring optimal bending geometry including conical parts. Designed for continuous operation, the VRM integrates Bendtronic control for maximum efficiency, redefining production standards in offshore wind and monopile construction. The robotic car wheel handling system at Zigant Automation Systems spans nearly 80 feet and utilizes 3 FANUC robots alongside motorized conveyor lanes to process palletized wheel sets. Robot number 1 manages pallet lids, dividers, bases, and protective packaging layers, removing and discarding them with vacuum grippers. Robot number 2 precisely transfers each wheel to designated conveyor lanes using vision-guided picking based on wheel center and product dimensions. At the system's opposite end, robot number 3 retrieves wheels from inventory lanes to fulfill downstream order requirements, ensuring efficient and accurate material handling throughout the process. Norzer manufactures high-quality springs using advanced CNC machinery. The process begins with the careful selection of premium spring and stainless steel wire. Compression springs, tension springs, and custom-shaped designs are produced using state-of-the-art machines from Wafios, Dorn, and OMD. These machines guarantee accuracy, enabling the production of springs with wire diameters ranging from 0.2 millimeters to 26 millimeters. Heat treatment furnaces enhance the mechanical properties of the springs, improving their strength and longevity. Surface finishing techniques, including delta tone coating, lacquering, and vacuum tempering, further optimize their performance for demanding applications. The Plauen facility, designed for efficiency, provides an expanded production area and modern work conditions. Rigorous quality control is ensured with specialized testing machines. The BendMac 3 roll plate bending machine ensures precise bending with independent roll control. For models with a roll diameter of 230 millimeters or more, all 3 rolls are powered by hydraulic motors and reducers. Smaller models use hydraulic motors for side rolls and a chain-driven upper roll. The system allows pre-bending on both sides without removing the plate, while a braking mechanism prevents sliding. Hardened rolls, a cone bending device, and dual rolling speeds enhance efficiency and reliability. This is Darastal's factory, which produces seamless rings from pre-forged blanks using 2 computer-controlled ring rolling mills. The process begins with forged and pierced discs, which serve as raw material. These blanks are rolled and compacted to precise contours for optimal properties. The combination of forging and rolling ensures a high degree of material integrity and homogeneous structure. A computerized process control system continuously monitors the rolling path, volume distribution, and dimensional accuracy. The rings are rolled seamlessly within tight tolerances, minimizing material waste, machining effort, and costs. The rolling force of both the radial and axial rolling stands reaches up to 250 tons. This allows for the production of rings up to 3,500 millimeters in outer diameter, 850 millimeters in height, 500 millimeters in wall thickness, and 8 tons in weight, used in gear manufacturing, bearings, and sealing applications. The repair process of a 15-ton press cylinder at Hydraulic Service Rhein-Ruhr follows a structured approach to minimize downtime. The cylinder is first removed from the press and transported to the Oberhausen facility, arriving at 2:30 a.m. Upon arrival, a detailed inspection is conducted to assess wear, damage, and necessary reconditioning steps. The component undergoes precision machining, honing, and seal replacement to restore optimal functionality. Once reconditioning is complete, assembly and testing commence to ensure performance under operational conditions. The hydraulic cylinder is subjected to pressure and leak tests to verify proper sealing and functionality. After passing all quality checks, reassembly begins promptly. The entire process, including inspection, repair, and testing, is completed within 3 business days. This efficient workflow ensures minimal downtime, allowing the press to return to service quickly with restored reliability and performance. Gearing production at Wikov involves the manufacturing of hobbed gears with external gearing up to 3,500 mm in diameter, module 32, and internal gearing up to 2,650 mm in diameter, module 25. Profile ground gears are produced with external or internal gearing up to 2,800 mm in diameter, module 34. These gears undergo in-house heat treatment processes, including gas carburizing, quench hardening, press quenching, and gas nitriding. Gas carburizing is performed for components up to 2,000 times 2,500 mm in size and 8,000 kilograms in weight, while quench hardening utilizes oil baths with capacities of 35,000 liters and 80,000 liters. Press quenching accommodates wheel diameters up to 1,200 millimeters with a maximum gear height of 250 millimeters. Heat treatment quality is verified through process control, checking the hardness of teeth, effective case depth, and microstructure. Dimensional inspections using coordinate measuring machines, CMM, such as Wenzel 3020-40 and Merlin 1100, ensure precise compliance with specifications. Teeth profile inspections, performed using Klingelnberg P100 and P300, confirm the accuracy of the gear profiles. Stringent quality control measures include chemical analysis with spectrotest, mechanical property testing through tensile and impact tests, and multiple non-destructive testing methods. Ultrasonic testing, UT, using Krautkammer USM35XS, detects undersurface cracks, while magnetic particle inspection, MPI, is used for detecting surface cracks. Post-grinding burned surface inspection, conducted with RollScan 300, guarantees the integrity of the finished product. After production and quality verification, final gearbox assembly is performed under controlled conditions to ensure precise component integration. Each gearbox undergoes comprehensive testing at a specialized development test facility. Running tests assess parameters such as temperature, pressure, sound levels, and vibrations, while load tests simulate real operating conditions with up to 8 megawatts of load. Gear units operating in extreme environments are subjected to cooling chamber tests, and rail vehicle gear units undergo dynamic load simulations to replicate real-world stresses. The Czech Republic boasts a robust gear and gearbox manufacturing industry integral to its economy and closely linked to its prominent automotive sector. In 2023, the Czech Republic exported approximately 25,000 tons of gears and gearing products, marking a 17% increase from the previous year. This export surge reflects an average annual growth rate of 8.4% from 2020 to 2023. The total export value in 2023 reached $331 million, up from $242 million in 2022, indicating a 12.5% annual growth over the same period. Germany emerged as the primary destination, importing 16,900 tons, followed by Poland, 1,600 tons, and Italy, 1,100 tons. The gearbox segment has experienced fluctuations. In 2022, production increased by 4.5% to 43 million units, ending a 3-year decline. However, this figure remains below the 2018 peak of 58 million units. In value terms, gearbox production rose to $676 million in 2022. Exports in 2022 totaled 31 million units, an 8% decrease from the previous year, with a total export value of $789 million. Spain and Germany were the leading importers, each receiving 8.4 million units, followed by Slovakia with 3.9 million units. The bearing and gear manufacturing industry in the Czech Republic generated revenues of 616.8 million euros in 2024, reflecting an annual growth rate of 3.2% from 2019 to 2024. The sector employed 7,768 individuals across 71 businesses, with employment growing at an annual rate of 3.8% during the same period. Notably, the Czech Republic ranks 13th in revenue, 9th in the number of businesses, and 10th in employment among 37 European countries in this industry. The Zany Motion Master 800 at Technia is an advanced 800-ton press designed for high-precision stamping processes. It enables both progressive and transfer stamping, ensuring versatility in production. The machine features a complex press system optimized for manufacturing shock absorber components like spring seats and lower brackets. Its automated zigzag feeding enhances material efficiency, reducing waste and costs. The press operates with high-speed precision, ensuring consistent part quality. The integration of this machine has improved production capacity, making Technia more competitive while maintaining high standards in stamping and welding. The seamless tube manufacturing process at ArcelorMittal begins with the arrival of raw materials. Steel billets, produced in a Czech Republic steel plant, are delivered to the facility, where their quality is verified. The billets are stored in the yard, segregated by type and heat, before being introduced into the rotary hearth furnace. The billets are cut to the required length and heated to approximately 1,250 degrees Celsius to prepare for forming. The hot billets proceed to the piercing stage, where they are transformed into hollow shells up to 11 meters long. The pierced billets then enter the premium quality finishing mill, PQF, employing advanced technology to ensure precise wall thickness control. Ultrasonic measurements continuously monitor and maintain strict tolerances. To achieve the required mechanical properties, the tubes undergo normalization in an induction furnace before passing through a 12-stand sizing mill. The tubes are rotated on a cooling bed to ensure straightness as they cool. At this stage, they can reach lengths of up to 42 meters before undergoing pre-finishing processes such as cutting, straightening, and inspection. The finishing process involves heat treatment, further inspections, and final processing to meet customer specifications. For oil country tubular goods, OCTG, tubes undergo upsetting, threading, and coupling installation, followed by non-destructive testing, such as magnetic flux leakage and ultrasonic inspection. Hydropressure testing ensures the integrity of each tube. Final steps include surface treatments, stenciling, and protective varnish application. The tubes are then bundled for transportation, ensuring safe delivery to customers. This advanced manufacturing process guarantees high-quality seamless tubes tailored to the needs of the energy sector. The Harvey Solid Endmill from Kennametal delivers exceptional performance through its advanced design features. A twisted cutting edge enhances corner stability, ensuring a soft cutting action even at high ramping angles. The precision-faceted eccentric relief reduces vibrations and friction, enabling smooth operation across multiple materials. Innovative chip gashes within the flute's lower cutting forces and improved chip evacuation, supporting efficient material removal. The tool's proprietary core design adds strength, allowing deep axial cuts with maximum stability. During side milling, the Harvey performs dynamic milling at 5% radial engagement with an axial depth of cut up to twice the tool's diameter. It also handles 60% radial engagement with a 1.75 times diameter axial depth. For slotting, the tool cuts up to twice its diameter, progressively increasing depths from 1D to 2D. It demonstrates precision and stability while cutting through 4,140 steel. The Harvey is also capable of plunging and ramping, handling angles up to 45 degrees with full radial engagement. Its continuous ramping motion highlights the tool's ability to maintain high performance under demanding conditions. From pellet to super strong steel, the SR steelmaking process. The foundation of cars, ships, battle tanks, railway power plants, towering buildings, and massive bridges begins with a small yet powerful pellet. At SR, the journey of transforming iron ore into super strong steel is a complex process. It starts deep in the iron ore mines, where rich deposits are excavated and processed at beneficiation plants in Bela Dila and Dabuna. The ore fines are enriched, converted into slurry, and transported through one of the world's longest pipelines, over 500 kilometers, to pellet plants in Visakhapatnam and Paradip. At the pellet plants, the slurry is refined into high-quality iron ore pellets. These pellets are then shipped to Hazira, SR's advanced steelmaking facility. Upon arrival, they are unloaded and directed to storage bays or directly fed into direct reduced iron, DRI, Corex, and blast furnace BF units. Through controlled chemical reactions involving reformed natural gas, limestone, coal, or coke, the pellets are reduced to molten iron or direct reduced iron. The molten iron is further refined in electric arc furnaces and KOBM converters, where impurities are removed to enhance strength and purity. In the ladle furnace, ferroalloys are introduced to achieve precise steel properties. Some grades undergo vacuum degassing to ensure low sulfur, phosphorus, and gas content. The purified steel is then cast into slabs through continuous slab casters. These slabs are reheated and processed in rolling mills, producing hot-rolled coils and plates. Depending on customer requirements, they may undergo further treatments, cold rolling, galvanizing, or coating to create the final product. The Seiko 335 disc milling cutter is engineered for precision and efficiency in large slot widths. Its advanced V-shaped insert concept optimizes cutting geometry, reducing cutting forces and noise while ensuring a secure connection between the insert and cutter body. In slotting operations, the cutter runs at a cutting speed of 165 meters per minute, engaging a 25 millimeters wide slot with high precision. The insert's 4 cutting edges enhance tool life and lower costs, while the wiper flat ensures a fine surface finish, eliminating the need for secondary processing. For half side and face milling, the cutter maintains stability with a controlled depth of cut, effectively machining C45 steel at 0.25 millimeters per tooth feed rate. The fixed pockets with central coolant provide efficient chip evacuation, while adjustable pockets offer flexibility for varying applications. Circular interpolation is executed with high accuracy, handling diameters from 200 to 220 millimeters. The cutter's robust design allows smooth material removal at 0.23 millimeters per tooth feed, maintaining consistency and precision. In face milling, the tool achieves a 100 millimeters cutting width with minimal vibration. The optimized cutting angles and grade selection ensure superior material removal, maximizing productivity in demanding applications. Kennametal's KenFeed 2X milling solution enhances high-feed machining with a single insert size, doubling cutting performance. Provides 6 cutting edges for superior material removal rates. The thick, robust insert design ensures reliability in demanding operations, including deep cavity milling up to 3XD. Available in multiple geometries for different materials, KenFeed 2X optimizes roughing operations with internal coolant tool bodies in screw-on, Endmill, and shell mill configurations, making it ideal for pocketing, ramping, and helical interpolation. Kennametal's beyond top-notch profiling turning platform delivers precision and efficiency in high-production profiling applications. Its inserts and tool holders ensure consistent performance, accurate indexing, and secure clamping, leading to superior surface finishes and extended tool life. Precision ground inserts reduce cutting forces and provide stability against alternating force directions. The second cutting edge remains protected from chip hammering, enhancing durability. Designed for turning operations in steel, cast iron, stainless steel, and high-temperature alloys, this system optimizes material removal and machining accuracy. Whether for grooving, cutoffs, or profiling, it ensures reliability and longevity in demanding metalworking environments. The heavy plate production process at Salzgitter begins with the manufacture of high-quality steel slabs. Pig iron from 3 blast furnaces is transported in torpedo ladles to the basic oxygen converter, where oxygen blasting removes impurities, transforming the iron into crude steel. Secondary metallurgy processes refine the composition through alloying, heating, and vacuum treatment. The molten steel is cast into slabs using advanced continuous casting machines. After cooling, the slabs undergo surface inspection before being transported to the rolling mill. They are loaded onto a pawl-type skid conveyor and measured using laser technology. The slabs are then heated in natural gas-fired pusher furnaces, where they remain for approximately 4 hours before moving to the rolling process. A discharging machine transfers the heated slabs to the roller table. The descaling spray removes oxidation by applying high-pressure water. The rolling process is controlled by an internally developed model, ensuring precise thickness tolerances. The slabs are compressed between work rolls supported by backup rolls, producing plates of 5 to 120 millimeters thickness and widths of 800 to 3,500 millimeters. Rolling forces reach up to 8,000 tons, and thickness is measured via isotope radiography. After rolling, the plate undergoes accelerated water cooling to achieve desired mechanical properties. Further processing includes hot leveling, marking, shearing, ultrasonic testing, and stamping for identification. Cold straightening corrects any residual stress. Heat treatment, such as annealing and quenching, enhances strength and wear resistance. Shot blasting and primer application protect the surface, while milling machines prepare weld edges. Additional processing, like bending, facilitates tank construction. The final product is tested for tensile strength, impact resistance, hardness, and microstructure composition. Plates are dispatched via rail or truck for just-in-time delivery, serving industries such as shipbuilding, construction, pipelines, and wind turbines. The transfer press with coil line from Dreyer Automation is an advanced system designed for high-efficiency production in the automotive industry. This fully automated solution integrates multiple processes, ensuring precision and productivity. The process begins with the coil line, which feeds high-tensile steel into the system. A coil straightener with single-roll adjustment prepares the material by eliminating any distortions, ensuring optimal flatness before stamping. Coil changes are executed in inching mode, allowing precise alignment and minimal downtime. Once the material enters the servo press, which has a press capacity of 8,000 kilonewtons, the transfer system moves the workpieces between forming stations. Manual rail couplings facilitate quick die changes, allowing flexible production. The entire system operates in automatic mode with an integrated control system based on Siemens Cymotion, ensuring seamless synchronization between the press, transfer system, and coil feed. Dreyer Automation's modular transfer technology provides flexibility across various press types, including eccentric, knuckle joint, hydraulic, and highly dynamic servo presses. With separate drive technology, movements are precisely coordinated, allowing high-speed production with reduced vibration and increased efficiency. Safety and energy efficiency are prioritized, with adaptive overload protection and energy recovery strategies minimizing wear and operational costs. The use of standardized components ensures long-term reliability and easy maintenance. The steel production process at Czech is undergoing a major transformation with the introduction of new environmentally friendly technologies. The company is replacing one of its two coal-based blast furnaces with a state-of-the-art electric arc furnace, EAF, which will significantly reduce carbon emissions. The EAF will melt scrap steel using electricity, increasing the plant's energy consumption by approximately 30% from the current 1 terawatt-hour, TWh. Construction of the new furnace is set to begin in 2026 and is expected to be completed by December 2028, with a production capacity of 1.3 million tons per year. To support the operation of the EAF, Czech will establish a high-voltage power supply system, including a transformer station. Additional infrastructure developments will include demolition work and the construction of new production halls. Alongside the furnace, the company is also building an emissions-free iron ore briquetting line, scheduled for completion in 2027. This project is partially financed by the Modernization Fund, covering more than half of the nearly 1 billion crown investment. Furthermore, a combined heat and power (CHP) plant using natural gas will be constructed to transition from coal-based electricity generation to a cleaner energy source. The CHP plant is expected to be operational by 2027, further enhancing the sustainability of the steel production process. The implementation of these new technologies is projected to reduce carbon dioxide emissions by 55% compared to 1990 levels. This strategic shift aligns with the European Green Deal, which aims for climate neutrality by 2050. By adopting low-emission steel production, Czech will avoid extreme costs associated with carbon emission allowances, ensuring the long-term sustainability of its operations. Despite these advancements, the European steel industry faces challenges such as global overproduction, declining demand, and high energy costs. In 2023, steel production in the EU fell by 10 million tons to 126 million tons. In the Czech Republic, crude steel production dropped by 30% in the first 3 quarters of the year, reaching 1.9 million tons. Třinec remains the largest steel producer in the country, following the closure of primary steelmaking at Liberty Ostrava. Since 1996, the company has invested over 10 billion crowns in environmental projects and 40 billion crowns in technological development. This latest investment of 25 billion crowns marks the largest steel industry upgrade in the Czech Republic since the 1980s, securing the future of sustainable steel production in Třinec. At ArcelorMittal Ostrava, the production of AMTB bars begins with continuously cast billets, measuring 130 or 180 millimeters. These billets are transported via roller conveyors to one of 2 walking beam furnaces. Once heated to the correct temperature, the material moves to the rolling line, where it undergoes descaling to remove surface scale. The billet is then shaped in rolling stands through multiple passes. The ends are trimmed using rotary shears before the bars acquire their final form. To ensure the required mechanical properties, the bars undergo controlled cooling in the temp core cooling system. After cooling, they are transported to cooling beds for gradual temperature reduction. Once fully cooled, the bars move to the cutting station, where they are cut to customer-specified lengths. The finished bars are then bundled according to customer requirements, labeled with identification tags, and stored for shipment. AMTB bars feature a continuous thread along their entire length, eliminating the need for additional threading after rolling. This process enhances strength and simplifies handling, making them ideal for construction, tunneling, and geotechnical applications. Their ease of use and high durability make them a preferred choice in infrastructure and mining projects worldwide. The oxygen lance cutting process is used for cutting large and heavy metal components, such as this 16-ton cast iron shaft. This technique utilizes an oxygen lance, a consumable steel tube, through which pure oxygen is fed at high pressure. The lance ignites at extreme temperatures, reaching over 2,500 degrees Celsius, which is sufficient to melt and oxidize metal upon contact. Operators, known as oxygen lancers, are trained to handle the lance with precision. A specialized oxygen lance holder provides stability and control during the process. The cutting operation begins by preheating the lance tip, then introducing a steady flow of oxygen to maintain combustion. As the lance burns, it produces an intense jet capable of penetrating thick metal, with an average burn time of 3.5 minutes per lance. This method is particularly effective for dismantling massive structures and cutting materials that are difficult to process with conventional tools. Proper training and safety measures are essential to ensure efficiency and operator protection during the cutting process. The Czech Republic's steel plate and profile production industry has faced notable challenges in recent years. In 2023, the country's steel production declined by 21.1% compared to 2022, totaling 3.4 million tons, the lowest output recorded by the steel union. This downturn is attributed to reduced demand and systemic issues such as high energy prices and inflation. Despite these challenges, efforts to modernize and enhance production capabilities are underway. For instance, Vitkovich Steel has invested in one of the largest cutting machines in the country, increasing its cut-shape production capacity by approximately 1/3. Additionally, companies like Voestalpine Profilform SRO specialize in manufacturing thin-walled steel sections, producing approximately 15,000 tons annually to meet regional demand. The industry continues to adapt by investing in advanced technologies and seeking sustainable practices to navigate economic and geopolitical challenges. Brightspan Building Systems manufactures most of the small parts required for assembling its buildings. Each part and subcomponent follows a production order accompanied by a blueprint. Manufacturing drawings, generated by the engineering department, ensure alignment with customer specifications. Quality checks are performed by welders to guarantee compliance with drawing specifications, whether through manual welding using fixtures or robotic welding for precision and consistency. A range of tools and processes are utilized in the facility for small part manufacturing. Webbing components are bent in-house using a CNC-controlled tube bending machine. Operators program the parts using advanced software to ensure precise fitting at the weld station. The facility can process tubing up to 1.5 inches in diameter and 170 inches in length within 90 seconds. To prepare parts for welding, ends are clipped using an iron worker, and production orders specify the material type and required operations. Cold saw processing accommodates pipes up to 4.5 inches in diameter and lengths of up to 48 feet. Round and square tubes for leg manufacturing undergo drilling with templates ensuring repeatability. Each part is self-checked and inspected by a quality technician before proceeding to the final weld station. The Epic and Genesis building series are assembled in large welding cells, where welders work in tandem to tack and weld trusses. 3-ton and 5-ton cranes assist in placing subcomponents and maneuvering trusses during welding. The largest Brightspan buildings can span up to 300 feet wide, necessitating precise fabrication for seamless installation. The D-roller plays a crucial role in manufacturing, capable of rolling pipes up to 4.5 inches in diameter and 0.25 inches thick. Operators program the roller to produce exact radii, ensuring uniformity. Quality verification is conducted using a control table with templates and gauges. Subcomponents, whether produced in-house or sourced from approved suppliers, undergo rigorous receiving inspections to verify dimensions and quantities. Truss assemblies are validated against structural drawings, and process control plans dictate additional checks depending on production run lengths. Final inspection procedures ensure compliance with weld quality standards before products are shipped for galvanizing or directly to customers. Quality technicians and supervisors hold certifications from CWB for Canadian markets, AWS for the US, ZE for Europe, and JIS for Japan. Brightspan welding cells accommodate a diverse range of parts, with subcomponents verified against production orders and blueprints before work begins. Shift-to-shift inspections maintain quality assurance. Structural weldments are executed in a flat position within small building cells, supported by a 1-ton crane. Visual management boards provide welders with necessary documentation, including production orders, blueprints, weld procedures, lockout procedures, and production targets. Every part produced is assigned a part number for easy identification during assembly. Truss stations use jigs, rotated manually or with a mechanical rotator. Once welding is completed, parts are cleaned, inspected, bundled to prevent damage, and transferred to quality assurance for final inspection. Brightspan maintains an inventory exceeding $4 million, ensuring rapid availability. Assembly fixtures hold parts in place while robotic systems tack weld components, followed by final robotic welding. Inspections confirm adherence to blueprint specifications. The large robotic welding system accommodates diverse products, processing both large and small building components. The Super Atlas model, spanning up to 108 feet wide, exemplifies Brightspan's capabilities. Subcomponents are verified, tack welded in fixtures, then removed for final welding with crane assistance. Post-welding inspections confirm weld integrity and dimensional accuracy before final quality checks. Bandsaws cut subcomponents to length and process hollow structural sections, HSS, which are hot-dipped galvanized before use in end walls. Sizes range from 4 by 4 inches to 12 by 12 inches. Templates ensure precise hole configurations. Swagging, primarily performed by suppliers, is also available in-house, reducing pipe diameters for seamless assembly. The Whitney Plasma Punch Table processes 5 by 10 foot steel sheets up to 0.5 inches thick, cutting and punching holes to exact specifications. Incoming parts are reviewed by quality technicians before welding. Purlins are processed in 2 stages. Hydraulic presses flatten pipe ends before an ironworker punches holes. Purlins, essential for truss support, are manufactured from pre-galvanized or hot-dipped galvanized material. The CNC-controlled plasma cutter profiles pipes for base rail foundation systems and stick webbing for large buildings. The parts cleaner removes mill scale, slag, and burrs in a 5-minute cycle before operator inspection. Once cleared, parts move to quality control for final assembly. Trusses are trucked to the galvanizing facility, undergoing a multi-step process to ensure longevity. Hot-dip galvanizing follows fabrication and welding, with trusses immersed in molten zinc for full coating. This approach prevents internal rusting, unlike pre-galvanized tubing, which risks corrosion at welded joints. Post-galvanization, trusses are returned for final inspection, following documented procedures. Separation posts prevent damage, while holes in mating surfaces are cleared for seamless field assembly. Each piece undergoes 100% inspection, with rough spots identified and smoothed using a pipe sander. Trusses are bundled with spacers and labeled, ensuring they are cleaned, inspected, and approved for shipment.